Okay, we'll continue to talk about optical flow. So just remind you guys what we are doing here. Like, let's show this demo code. I just grabbed it from OpenCV actually. Like this OpenCV tutorial. Not tutorial. That's just in the documentation there. Let's see where is it. So, but anyway, like this is what we were talking about. Like last time, it's like you want to check like what is your visually seeing. Like it's like therefore like they call it optical flow. It's like apparently what like in terms of appearance, like what these pixels are moving or something like this. So this one is like it's not dense. Actually, this is using the Lucas-Calendar algorithm we talked about last time, and it only checked like some of the pixels there. So initially, like I don't know why this paused or something. Oh, okay. Oh, actually it hangs for some reason. So anyway, this one it kind of like gets some good features to check. I'm not sure the function. I look at the documentation there. It looks like it's just like doing some color detection, and that determines like some good features to check. Here it only check those features there. I'm using the Lucas-Calendar as I mentioned. So, but let's continue what we talked about. Like we are talking about the Schunck method. So another algorithm. So I like to go through that in more details. So it used. It's formulated this way. So if you remember last time, like basically, we have these pixels, right? So like we have like two images. So or like a sequence of images. You look at consecutive frames. So you have image, and then you have like some pixel is moving around. I move tiny a little bit, like from here to here. So we make. So we want to see like how these like pixels move, basically, and if you remember, like we need to make some assumptions there. I'm not sure anyone can remember some of those assumptions there. Like we need a couple assumptions in order to find the flow of these pixels. So anyone? I don't know. Isabel, can you help? You always remember. It's okay. I mean, like you remember, like there's some assumptions, like when we try to
about, like,
derive this optical flow.
Yeah. Spatial coherence.
Yes. Oh, you're so good. Actually, I don't even remember the name about it. Yeah, spatial coherence. It's saying like this pixel, like if this move here, like the neighborhoods also move around, like. Yes, there's okay. The color doesn't change, or like the intensity doesn't change that much. We assume this pixel move from here to here. The intensity doesn't change much. Like they call it what? Brightness, constancy, something like that. And the next one is like just a small motion. Assume the motion is small, basically. So from here to here, like a tiny motion. So with these two, last time we said that like we can derive a constraint that basically saying that if I have this flow is basically this disparity is U and V. So of course this disparity like depends on like where you are. So like U and V itself is like a function. Like you have U x y, V x y, something like this is like the horizontal and vertical. Yeah.
Does brightness constancy have to be that particular pixel that's been identified, or should it be the neighborhood around it? If you're going to fluctuate brightness,
yes, this is assumptions. This is like kind of assumptions. Like so, it can be violated. So, for example, if you think of the spatial coherence, you say like here, I mean like it's not perfect. So, but we assume that. So, yeah.
I'm just asking for the algorithm's sake. Is it talking about constancy with a particular pixel or the neighborhood?
Oh, okay. It's all pixels basically. If you think of like each of the pixels can move around,
Okay.
all of the pixels I assume from here move to here. The the brightness or like the intensity doesn't change, or doesn't change much. So if we use that, like if we have the flow is like U and V, like basically like, and then last time we say that it is easy to derive using Taylor series expansion, that we have the gradient of the image Ix times U plus Iy times V plus It is equal to 0, something like that. So so it's basically just Taylor series expansion. So we expand this guy after we have a motion like this. We look at like what is this guy after this parity U and V, and then we subtract this guy with the first order approximation of this guy. And if this two has to be matched, then so therefore we set these to 0, then it will just get something like this basically. And then like for the spatial coherent, we can say like the change of U, so we can say the gradient of U, or like that's basically the partial U, or like I will just write Ux Uy. So that's the partial derivative of U in the x direction and in the y direction. So I want to have the norms there to be small. So plus like also V kind of close to 0, something like that. So to be small, maybe not exactly 0. So then like we say the okay, I guess what I can do is I can just shrink everything. See if I can do that. Yeah, then I will have some space here. So then the Schunck, I'm not sure is that how I pronounce that, Schunck method is basically I try to minimize. I introduce some energy function. After energy function is something like it's an integration over. I have this basically sum of this. I take both of them as a cost function here. So I just kind of weighted sum them together. So I have like Ixu plus Iyv plus It, and plus like say like weighted by some alpha here, the norm of U's plus norm of V. So something like that. I just try to minimize that. So I kind of integrate over everywhere. So like I want for the entire image, this is just sum up to be small. Does it make sense? It's just a reasonable formulation. I want to go a little bit detailed for this one because it's not just for this problem. Like, this is some very common problem like in engineering. So you're trying to minimize. If you look at this, what I have is like this itself, I can call it a function L, let's say. So I'm integrating like this energy function is just an integral of this L. And this L is like, I'm interested in, okay, I'm trying to minimize this E in terms of U and V, right? And U and V itself is like kind of a function because like it varies like at each pixels, right? It's like a function. So I'm minimizing a function of a function, something like that. So mathematically, sometimes they call it a functional, but we don't actually need to worry too much about that. Like, what I should say, like in terms of the terminology, but this actually can be tackled like in first principle. So if you think of this is like something like in terms of U, V. I want to be careful here. Like this is actually also a function of Ux and Vx, something like that, right? And also Uy and Vy. So it's actually a multivariate function. And I want to actually minimize over UV, but actually it also did UV, I mean Ux, Vx, like Uy, Vy also like kind of depend on UV. I mean like the whole thing I can think of like this is all kind of like independent variable. Then I can take a derivative, kind of like partial derivative. I can expand this, or like in the sense like therefore E also like is also a function of all these like U, V, ux, vx, uy, vy. Now, how do I minimize that? Like I basically I want to minimize from the uv such that I minimize this e, and one way to think of that, if just think of like we are doing calculus. So again, like even though e is really a function of function, but it's still like you think of like e is a some function in some high dimensional space. Still, the maximum will be like somewhere like at the maximum there. If you make some changes for uv, the values shouldn't change. Of course, it will change, but the rate of changing it should be close to zero. What I mean is like if I think of this whole thing like I put it as a parameter, okay, random parameter. Just at this moment, I say this call it w here. So if this is the optimum now, I have w at this pace is optimum. If I change this a little bit, let's say I consider e w plus some very tiny epsilon per some w tilde, and this w tilde can be anything. I don't care about what is that. But the change of this from this guy here, so what I mean EW plus epsilon W tilde minus EW, if I over epsilon, this is kind of like the definition of a derivative, right? This as like epsilon to be very small, this goes to zero, right? This is kind of general. It's general, like for it's. Only difference now is like this is almost like calculus, like you took derivative here. The only difference now is like my variable here, this w is actually a function itself. So it's actually essentially infinite dimension objects. So, but it doesn't really matter. So what?
You can use Lagrange equation and we're good.
Yes. Yes, but how many of you know Euler-Lagrange equations? Oh, yeah. So, actually, it's not bad. Actually, this is not bad. I mean, like this is exactly like, yeah, you understand. This is like you derive the Euler-Lagrange equation essentially. So, then like so. Okay, as I said here, like so, then this guy, then I can, okay, then I can just do a Taylor series expansion for this guy, right? So I can write E as like for this guy here, I can say U if I consider U plus epsilon U tilde, V plus epsilon V tilde, and so on and so forth like that. More variables here, there are 4 more variables here. This will be kind of equal to EU V UX VX UY VY plus I have a partial derivative of E with respect to U times epsilon U tilde, right? And then I plus E with like V epsilon V tilde and so on and so forth. I have also like UX epsilon UX tilde, so on and so forth. Like that, there are like basically 6 more terms here. I mean 3 more terms here. Now then, like I can this guy is like here, right? I can this subtract like let's say E U V UX VX UY VX VY here. So then what I left is just like partial derivative of E partial U epsilon U tilde. I mean this thing is equal to 0. Just have like this is equal to 0, something like that. Maybe I write a couple more terms just make sure you are not lost. So on. And then and of course E is a really integral of this L, right, over dx dy. And note that I'm integrating over dx dy, right? So this is actually I can my derivative here actually can go inside. I'm not integrating over u or something like that. I'm integrating some other variables, some dummy variables. So my derivative can get inside. So actually this is equal to I integrate, that's partial L, partial u. I can put this epsilon u tilde, something like partial L, partial v tilde, so on and so forth. Actually, maybe I write a couple more times again. Partial L, partial ux tilde, and so on. I can say 4 more, let's say 1, 2, 3, yeah, 3 more terms is equal to 0. Now, let's see. Now, of course, L is this guy here. So L is this guy. So if I take the derivative of u here, only this part depends on u, right? This depends on ux here. So therefore, taking derivative of u here, I guess ix here. Something like, actually I have a square, actually I got 2ix. Actually, it's more than that. I equal to 2ix plus isu plus iyv plus it times u.
No, times ix.
Oh yeah, sorry. Times ix, yeah. Thank you. Times ix. And v is similar. If I look at this guy here, is equal, of course I should multiply epsilon u tilde here. And then this guy is similar. I have epsilon times v tilde. This derivative will be again 2 times ixu plus iyv plus it times iy there. So let me do one more case here just for this guy. So I have this time I take derivative with respect to ux here. So there's no ux here. This one is actually equal to ux squared plus uy squared, right? I mean, this is vx squared plus vy squared. So therefore this guy here is equal to alpha ux 2ux times basically just 2ux, yeah. So it looked ugly. I guess I just go back to my slides now. So that's what we had just now. So I have if I just look at this guy, I take the partial derivative for this one. Then I have this bunch of terms here. I take derivative of this one here, right, with respect to u. So I have these 2 times this guy times this one here. Times ixu actually. But then I also have taking derivative of this guy here. Then I have the same guy here multiplied by iy v tilde. So then I just group together. And for the rest of these 4 terms I can group together again like this. So then this should be, and this is for L, and then I want to take the integral to be 0. So then basically say integrating this guy is equal to 0. So I have the epsilon here got cancel. After 2 here, I don't care because it's just a constant. So eventually I got this one here. And then if you look at this here, I'm close to be there, but I'm trying to optimize over U and V, right? Here, I mean, I want to, oh yeah, actually not yet. So I want to optimize over U and V, but I have some U tilde, V tilde here. So I want to eliminate some of this U tilde X and U tilde Y here. So what I can do is I can do some integration by part. I can absorb this U tilde X somehow, like inside. And then if you know like integration by part, I can shift that around. Then like, I will have like UXX instead. So that's exactly what we can do. So here using integration by part, I can absorb like this. I want to remove this U tilde X here. So I kind of like, one means maybe I just go for one terms here. Or like maybe I try to. Here I need to be careful not to. So what I mean is I can absorb that. I mean this U tilde X dx here is essentially equal to like du tilde dx, right? Something like that. Or like you can write partial also like dy something. So and then I have ux alpha square. This I'm looking just the first term here. So then like I use integration by part. I will get like ux u tilde alpha square. Maybe I ignore this dy for the moment. Minus u tilde alpha square uxx, right? Take the second derivative dx, something like that. This line, forget this line. I don't know how. Yeah. So then eventually like this guy, because of boundary condition is equal to 0. So then like I should have this instead. So then now you see like I only have u tilde and v tilde. Then I can group them together. It's actually I got this. So eventually remember that like I'm moving in any direction like for u tilde v tilde, and therefore like since this is arbitrary, for this integral to be equal to 0, so I have to have these two guys is equal to 0. So therefore like this I have this. So that's essentially like the Euler-Lagrange equation is what's that. So then yeah. Then let's see. We have these two equations here, and okay, in practical like implementation here. So I want to find this u and v here, right? So I for this ix iy, just as usual, we can compute that using filter. So I can have like ix iy is oh, I didn't show the filter there. But like for the Laplacian of like u and v, we can approximate the Laplacian operator as the mean of the u. It's like a Mexican hat minus the central location there. So if we do that, then like then we'll replace again like this Laplacian equal to this guy here. So then we move things around. Finally, we have an equation like that. So we find uv. Again, we will have a set of linear equations, like just two equations here. We can solve uv with something like that. So we can do it like iteratively, basically. Like you compute like ix, iy, or the gradient, also like it, like just like from the current frame, subtract the last frame, and so on. And then like you can start with like an estimate of u and v, maybe just all zeros, then solve this equation, then iteratively, like you can compute the U, the average of U again, and then repeatedly. So just mention a refinement of this function method that called the Michael-Bax method. It basically just like make a slight variation. I won't go into detail, but replacing this. If you look at the constraint here, so it have kind of a regularization term or like a penalty. It's like getting a kind of second order quadratic like penalty. So we replace the quadratic penalty like this function by this guy instead. So I don't know how to describe this function. I don't have a formula for that one. But here, if you think of this, this is a u x squared plus uy squared, right? And also like plus vx squared plus vy squared, something like that. But this guy, I don't know what kind of function, but it's a function of some, again, ux, uy, and vx, vy. But it's just saturated somehow when it's like ux and uy are quite far away, or like it's getting quite big. So why you think this would be better? Like any guess for this one? Yes, I think you are. Yes, the penalty may be too much for this guy because like the spatial coherence principle, like we make the assumption here, have this spatial coherence, but you think of like it's essentially if you have object here, if you have a boundary of the object, like at the boundary it doesn't hold, right? So definitely the change here, the gradient here will be infinite, if you think of that. So so if you make the boundary, say, I mean, with this really large penalty, like your at that, I mean your ux, uy, and so on, like will be pretty big and just not ideal in those cases. So, but anyway, just a remark. And now I would only also talk about one more method, and like that's the end for like optical flow. This method, like I'd like to mention that because like this is actually the one used in open theory. So it's a more recent method called like Gunnar Farneback. So it uses a rather how extreme assumption. So it assumes that like the image take a real form here. It will just assume the image which can be like represented in a quadratic form. So like these are the basically the pixel density, right? You think of like this is kind of like grayscale image, and then x is just the location of the pixel. Then I assume that the image like can be represented in a quadratic equation. So it's kind of like quite crazy to think of that because the only image it can represent would be like some kind of, I don't know, would be like you have a kind of bright region like it's going like darker like at the boundary, like something like okay represent something like that. But of course, this is only a approximation, and also like we can assume that A and B will change over kind of like spatially as we move around, like. But also, like we can assume that A and B doesn't change too quickly. So similarly, I can think of like another image also like have the same form there, like also like again I want to remove this. So if I assume that here is the same form, so basically like from image 1 to image 2 is just like I have a disparity D here, so therefore image 2 can be represented as this one, like F1, but shifted by D here. So then I substitute X plus D into the equation there, then I will have actually I should write this x minus d instead, right? So it doesn't matter. So x minus d here is equal to this guy here. So then if I re-expand that, eventually we'll just get like compare these two guys here. So the second order is the same. So I have the same term here, but for the first order, with respect to x, I have like b1 here is equal to, now in the second image, you can do this guy here, right? So I want this 2 to be this, actually, this would be, I can call it b2 for the second image. I want this b2 transpose equal to this guy here, so therefore I will have this one here, right? So, and of course I can just write it. So then I want to solve for the disparity, then simply d will be just equal to this guy here. Right? And my delta b here will be just like 1/2 or like minus 1/2 b2 minus b1. So kind of like actually that's a very nice work where you think of that you start with a crazy assumption and then try to derive it anyway. So then you relax the assumption a little bit again. So next step you think, okay, this is of course super crazy, right? So then I need to make sure that like A and B is actually can vary over like different pixels as well. So then I can make A and B like okay, B is like is vary over function, and also A here, I'll just take the average over the two images for the A. So I have A now is like the average of A1 and A2, but again, as I emphasize, like this A and B can vary like for different pixels. But of course, I have this spatial varying constraint. So I come back. I mean the spatial coherence constraint. I come back like the relax the constraint too much, then I pull it back again. So I will assume like this doesn't change too quickly. So then I can impose a window or something like that. I'll just say for over the window, I have the same D here. So as you can see here, like I basically, my assumption is that over a range of neighborhood of like X here, they share the same D here. And I can implement that with a window. So I have a W here, say something like, again, like a Gaussian like windows, it just get smaller as I go away from the origin. So then with this, again, we can minimize that. You can easily derive that this is like if you take the derivative as we did it multiple times. So you should get something like this. This is like similar to a kind of like, okay. If you look at this here, this one is very much similar to what we see multiple times, A transpose A inverse times A transpose, right? The pseudo inverse, but it's just pseudo inverse weighted sum, but with this W here. Yeah.
I went back over your corner detection video this morning, and that's where I think you introduced having the window W with like X, I guess, in an equation, and you said it was bad notation, but you never really cleared up what it meant. What does it mean
the slides.
What does it mean to have a window in an equation like that? Is that just a matrix of intensity values?
Okay.
5 by 5 or 2 by 10, or?
Yes. So if you look at this one here, my W can be something like this. So basically, maybe I write it like this. Okay. This is so. I don't know. This is like what version of. I must be missing something. Like this have been here. Like was a PowerPoint for so many years. They should have like something that Control C or something. I don't know why. So anyway, for the windows, I can define this W. Let's say as let's say if I xy, let's say wxy is equal to 1 if x x is less than equal to 3 or something like y, and y is less than equal to 3, and still otherwise. this will give me kind of like a window of 7 by 7 or something like that, right? Yeah. So this can be a window, something like that. And of course, I can have a better decay in the sense that near the boundary, I can have like closer to 0. So you can use a Gaussian function. So for example, I can have like Wxy is equal to exponential like x no control C again y square. I don't need a double, but yeah, something like that, right? Yeah. So I can have a window.
So it's only a thresholding device then. It's
just something like that. But I can. So windows can be more general than a threshold because I right here I make it smooth as I go to the boundary. I can make it smoother. So, but you can do something like that also. So if I do this, then exactly I'm saying, okay, I will basically share the same disparity, like from here up to like 3 pixels away, kind of. Yeah. But this one I will allow a more smooth decay. I mean, for the lower one here, if I use a Windows ID. Yeah. So, okay. Any other questions? So, okay. So I can solve D like this. Then I have to solve D like this, and a small modification is that again, like actually this is not the only algorithm I can do it. Like for all this optical flow algorithm, I can do this multiple times as an iteration. So just iterative refinement. So let's say I run it one time, I find the disparity somehow equal to this D tutor here. So then I can now I know what's the disparity, approximate disparity of the first one and the second one. Then I can shift the second one by this D tutor. I can update this A as A1x plus A2x plus this D tutor. I mean the mean of these two instead of A1x and A2x. And because my D here is actually equal to my delta B here. Wait a sec. Yeah, here actually I'm missing a. I'm missing an A inverse or something like that. So because my delta B is equal to if you remember, my delta B is equal to this guy here. So if I shift the this A2 by this kind of pi disparity D tutor here, I need to modify this delta B a little bit also. So I need to add this term for adjustment. So therefore, eventually I will have in the next iteration I will have delta B replaced by this guy, add this guy, and also my AX replaced by this guy here. Then I can repeat the same procedure again, and then again. So I can get a better and better refinement. So this one thing. So a final thing about this algorithm is a little bit weird, but it's mentioned in this paper that you can further parameterize your displacement using a kind of quadratic function like this. I find it quite mysterious why they take this form somehow, but they took this form. So if you do that, then your D now is parameterized by this P, with this guy. So I have this S. So basically D can be written as SP here. So then the formulation will change a little bit. Again, if you substitute D with SP, so you get something like that. Now instead of trying to solve for D, you solve for P instead. So therefore you can't solve a function like that. So once you solve P, of course you can get back D there. So that's the Gunnar Farneback. So okay, last thing I like to mention for the optical flow is remember we have these 3 assumptions. The second one is we assume a small motion, But in reality, like you have like objects in front and then at the back. Like at the back, the change will be a little bit smaller, but in front will like change more. Right? So if you want to adjust for that, like a reasonable approach, we can do it with pyramid again. So basically, for example, in this scene here, like okay, yeah, you see like the tree in the front will move like a bit more. Right? So what we can do is like we can do a multi-layer. So just do a pyramid over the entire image. So as we so like you can like do a kind of like pyramid of like we mentioned previously. So we have the original image, like both images we work on pyramid. Then we start with the highest level. So that's the kind of like the lowest resolution, and try to find the disparity there. And then once we find the disparity for that one, then we can like just warp the next one, right? So we know like how much this guy move approximately, and we can use this guy and warp this one, and then like use this one and this one. I mean, after the warp image, use this warp image instead of the original image to compute the disparity again, and continue to do that right? Level by level. So then I will get better, much better. Like for example, like for that video that we just showed you. So even though we only have two couple shots there. So but with the pyramid, like you can get much better results. So this is without the pyramid, and this one is like with the pyramid. Okay, that's about all I like to. Okay, there's some applications. This is kind of like cool, so I just leave it here. So like you find you get the basically like you get all the motion there. Then after estimating model, then you can get the Planck curve and so on. Of course, that one you need to get some knowledge how to estimate the camera locations as well. And apparently you can do something like background subtraction. If your camera is steady, then like once you catch like what's this moving, then it's very easy to know like what is the foreground and what's the background. And you can do segmentation and motion segmentation. It's basically the same principle as like foreground kind of like estimation. You can do tracking, apparently, and also like recognizing events, like based on like how someone moved, then you can model like, okay, this is dancing and this is jumping and so on and so forth. So, but I don't know. This is like kind of old paper, probably not the state of the art now. So maybe like last line just for fun. This is like what? So it's like kind of optical flow without motion. So I am a bit kind of early. Let me show you some of this code. So this I just showed this one of this demo, that one. So this one. So see another one. Let's see. This is also extract from Open Series. So see this one. Let's see this one. So the first one I showed you like earlier is like using the Lucas calendar. That's the one we discussed last time, and also like with the pyramid. That one is not so quick. So as you can see, like it only select some of the point to check. If you use the Farneback, that one is actually a bit quicker. So it's like real-time tracking like a video. I don't know whether it's showing the video as well. No, it didn't. So that's someone. The original video is like someone's move. Let's see if I maybe. So it's basically someone is moving around. The color here is a it's showing HSV in HSV color domain. So I think the color is showing the brightness probably is the speed, and then the color is the direction. The hue is the direction. So direction of moving. And actually I also extract this part, like try it on the camera. So let's see. But it seems like this is quite easy to crash though. Let's see, I have like camera 1. So again, like this guy is I was trying not to shoot you guys, but oh, wait a sec, what's that? Okay, yeah, that's the Farneback with the Farneback with the. It's hard for me to hold steady, I guess. I'm also, I guess maybe I should choose something is a little bit more steady. Okay, just put it here.
Which method is this?
This is the last one I talk about, the Farneback. Yeah, that's use the crazy assumption right at the beginning. So this one can do kind of real time for the entire image, kind of. So, but for the current, I don't think it can. Let's see. Oh, this one okay. Let's do. Oh, wait a second. Okay, yeah. I need to change my camera. So it's kind of to check like some of this. It's checking okay. So you can use that to check out potentially. But I kind of like move this web pawn. I pick up this web pawn. I pink pawns there. I pick up another couple of cyan pawns. So anyway, oops.
How difficult would it be for to also include detecting the same movement, like that's detecting different corners, but they have the same movement, that is the same object. So instead of showing like 5 lines moving, maybe just condense to 1. Would that be like difficult?
I don't quite get the question, honestly. So you said like for the same object like here, you want to get just 1 pawn, like instead of like.
Well, it's fine that there is 5, but maybe just show 1 and somehow detect that that's 1 moving object instead of 5 different ones.
It's like localizing the object and then
That
tracking it to 1 point as opposed to 5 lines.
Yeah.
I guess the problem here, like I didn't track a lot on this code here, so I don't know how well like use a OpenCV function here, so called like I don't know whether you can see it. This like good feature to check. So I'm not sure if I just use a corner detector like to arbitrarily grab a pawn, how good it is tracking that. So, but I assume it shouldn't be too bad, but
You have to include image warping though too, right?
yes, but because you're frame by frame tracking, right? So if you are not moving too quickly, or like if you don't kind of like, it should be okay. I mean, like if you the resolution is high, but the problem is like you need to decide what. For example, like if you use the current method, then apparently you can only track a limited number of pawns, I guess. So, but of course you can try this like the third method here, like the Farneback, to check all the pawns. But in terms of localizing the object, like, I'm not sure like that. I'm lost actually. Can you repeat the question again? No. Seriously, like.
It's more like if
Yeah.
we wanted to apply this to an employment situation and your boss says, hey, I need you to track this object, he doesn't, or she doesn't want to see 10 different lines going all over the screen.
Oh,
It's one.
then you need to recognize that object first, right?
Yeah.
So that's the. You will need additional module just to recognize that object first. Determine, okay, this is my target object, then I can
So you
focus
need to
on.
recognize first and
Yeah.
then track. Okay.
Yeah. So, and yeah. So any other questions? Yeah.
What are those parameters that go in the optical function?
Yeah. What's that again?
I think the flow function that you have, like the flow, calculate optical flow for,
This one?
yeah.
Uh-huh.
What are those parameters?
You mean the parameters or like what?
Yeah, the parameters that those, like the arguments of that function.
Oh yeah. That one I can't remember that. We need to look at the. Yes. Yeah, that you have the it use the pyramid also, so you have the level of pyramid, window size, iterations. So basically is that. Let's see. The first image, second image, flow I think is a restful. Flow should be like the previous estimate, I think. So and then you have the pyramid scale, like so each time you, okay, I don't know. Maybe I can. That will, yeah, that's difficult. Actually, I should just copy this here and work. Why it didn't copy? I didn't. Okay. So yeah, it's easy to see it now. So.
Or like, maybe like how do we determine the value of each one of them? Do we just like put?
Yeah, I guess you put the default here. So for example, like the scale like 0.5 is make quite a lot of sense, I guess. Right? Number of level of 3, I think it can make sense also. Maybe you can adjust this window size there. Yeah. So number of iteration, I don't think it matters that much. Yeah, you can try that out. Like, yeah, pay on that. Yeah. So. Yeah. Anyway, I guess like all this, whenever you get into a function like this, you just need to take a look of the documentation and then like maybe even search in Google is nice. Like just what parameters are nice or something. Yeah. And so any other questions? So maybe I mentioned a little bit the homework again, like so you guys see that I. Okay, put up the new homework. Where is that? Yeah. Okay. This one is there. So anyone besides Logan, I look at the homework. Yeah. So basically. I want you to implement the fine homography function, And as an extra bonus, the extra credit, you can also implement the WANSEC also. So, if you implement the WANSEC, it's likely that your solution will be more stable. So this well, Logan told me that I may have bug in this one. I'm not sure. So it's like alpha version. I made it this year, so I'm not sure that. But it works. It works for my image here. So, and I try to flip the image. It still works. So it seems to be.
I do have a question about that line, the last line right there where it says match XY.
Here.
Yeah. What is the query index or query IDX?
Yeah, that's how you use this. The query index is the index. Okay. When you do matching, you have two images, right? So one is the query, one is the train, basically. The index is just that you have the list of the indexes, and then it's just like which one is matched to which one. For example, if you have 3, 2, so it's like 3 matched to 2, something like that. So
it goes through.
So then
it goes through each match and checks.
Yes, because you input, you get you give them like the list of the descriptor, right? Yeah, list of descriptors there. You give them the list of descriptor, and we didn't specify the location, so I need to get back the location. So that's why.
Right, which is what that line is for.
Yeah.
Okay.
So yeah, it shouldn't be very hard, but you the fun part, the tricky part usually is debugging. Like you very easy to write like in half an hour, or then like you take like 10 more times to on the debugging or something like that. So, and honestly, like in real world, like you have a problem like this, like you may need to even like write code just to write some tools to help you debug, basically. Or like for example, like when I wrote the MATLAB version of this thing, like this time I'm quite lucky. I do it like first time, like it's okay. If not, then like I need to write code just to display like how the matches are. Then I need to go down like and try different cases. Okay, if I just grab these several matches that I know exactly they match well, I try to compute using a homography. I know it should give me good result, and so I need to do some hand picking of data like that. But I don't know. By the way, like I think I'm at that part I was pretty smart when I write this. I'm sorry to just praise myself for that. So do you know how to match this? Just think of that. Like you have these two images, right? I want one image and my another image. If I just add them together, then this part will now I really adding them together, right? So this part, like I will have like the brightness will be double, right? Mm-hmm. So how did I do that? Or like how do you think like you should do that? Like if you have a problem like this.
Filter it.
Yeah. What?
Filter it.
No, you don't want to filter it.
I think you'll add them and go to the array, like the output, and see that ones with the highest like intensities, like that's the highest intensities, and then you'll keep like narrowing down your search till you have like those like elements with the highest intensity.
No, that is a bit too complicated and more. I probably won't work. Wouldn't
you just put parts of one image and parts of the other image into a third array, and just select one or the other?
So just use one and don't use. Then you need to realize which one they are overlapping, right? this is very complicated problem actually. If you need to realize whether this part I'm overlapping, which part I'm not overlapping. Okay, I would just say you should normalize that, right? So this part I should overlapping region, I should over by 2. For the west, I'm not overlapping by 2, right? Reasonable, right? So just for this part here, I should be like divided by 2, and then the west I should not divide by 2, right? But how do I do that? For that part, I still need to know where I'm overlapping, right? Okay, you guys can think about it. Of course, the answer is in the code. Okay, I'll see you guys like Thursday.